Thank you, folks, for joining this talk. So essentially, we'll be looking at an introduction to hardware hacking. Uh, I think uh, one thing I'll tell you is that hardware is like super interesting, and the reason is that controlling something physically with software, it kind of gives you a kick any day, right? And that's always fascinated me. And if you really look at it, right, it's been like a huge dream for humanity in a way, right? How do I like control something? How do I make something make decisions on its own and all of that? I think that's really, really cool stuff, right? And hardware kind of allows you to do that, right? But as software engineers who generally used to programming large systems and all of that, right? Servers and and all that, hardware can kind of seem a little bit weird in the beginning, but it's not that it's not that difficult at all, right? So generally we feel, when we think about computers, this is how we think they look. You can think about a laptop or a desktop machine, for example, right? But then again, if you this is a server on the left side, or on the right side is a Raspberry Pi, right? This is how we are used to thinking of them. But in general, you don't have to think of computers as being like this, right? Any piece of any CPU that can kind of you know um, tell you how allows you to control anything, making decisions, or kind of looping and doing something interesting, right? Those are all computers. And one more thing we usually forget is how many, within double quotes, computers are really there, within a what we call like a regular computer, right? For example, take a desktop machine, right? Within a desktop machine, there's probably dozens and dozens of within double quotes computers, right? For example, the controller chip on hard drives is a computer on its in its own right, for example, right? And there's so many computers in your car, for example, right? Even in two-wheelers these days, right? A lot of decisions are made by these little computers, right? And all these computers can be programmed, and then it's not very difficult to program them either, because back in the day, for example, when I started out with embedded systems, and we had like 4 kilobytes of flash memory and 1 kilobyte of RAM and all that. But it's become a lot more generous these days, right? As technology as technology goes forward, we have a lot more capability even in very, very small computers, right? And you'll be very surprised how simple it is actually to program these computers, right? That's what I want to show to you today. And to prove the point that hardware is not difficult, I'm starting with almost like a bare circuit. As you can see, there's probably just a board on a breadboard, the Raspberry Pi Pico. The Raspberry Pi Pico is incredibly cheap. It's less than 300 rupees. You can get it from Amazon or robo.in or wherever you get electronic components. And be- and I'll be building fairly decent circuits live, right? I mean, I'm not even built the circuit yet. So if I'm able to build it live, I mean, obviously you should be able to do it as well. It's not a big deal at all. And if you have enough time, you can build something really complicated as well, right? Now, we will be especially talking about microcontrollers today, not so much about what we generally call CPUs, right? Now, this is one of the very early Intel CPUs. It's called the 8086 CPU. If you look at the CPU, right, I mean, look at how the pins are named. So you have a lot of pins starting with AD, and that's like address and data pins, like right? And then you have some other pins like for syncing and non-maskable interrupts and clock and other pins, right? Now, however, CPUs are they are mostly like, they have dedicated chips for dedicated pins on the chip for every function, right? But microcontrollers are actually very different. They pack a lot of punch. To make a CPU work, you need a lot other circuitry. For example, to make a CPU work, CPU doesn't have any RAM, for example, right? You would have to first connect a RAM and then take all the address and data lines and connect them to a RAM. And then for input, you need to figure something out. For output, you need to figure something out. And in general, what happens is that CPUs generally have very, very few interrupt pins. For example, you can see here that there is a pin named interrupt, and there's like a single pin, right? And then every hardware device needs to interrupt the CPU. For example, a hard disk and Ethernet card and a keyboard and mouse and all of that, right? So what happens is that there's extra circuitry required. So there's something called a programmable interrupt controller that will generally interrupt the CPU, right? And then the software needs to ask the programmable interrupt controller, hey, hey chip, who really interrupted you? And then accordingly, the operating system figures out. For example, if the keyboard interrupted the programmable interrupt controller, then the operating system will run the keyboard interrupt handler, and then it will figure out which keys were pressed, for example, right? Of course, this all happens really, really fast. But then again, the whole point is that the CPU is highly what is specialized, and then it is very sparse in what it has. It's practically only the central processing unit within the CPU, that's like the core, right? And what really happens is that you need to provide it with a lot of other chips for it even to start looking like a computer that you really know about, right? That's kind of how CPUs work. But when it comes to a microcontroller, you can see that microcontrollers have, like, for example, this particular microcontroller, the ATMega8 or 48 or 88. These are 28 pin microcontrollers. For example, pin number 1 starts here, and then you wrap around to go up to pin number 28. But then again, these pins are actually they have multiple capabilities, right? Like, don't worry about if you don't understand any of this. Don't really worry about it. But all I'm trying to tell you is that, hey, a CPU has very, very pins that have dedicated purposes, whereas microcontrollers have pins that can do more than one thing, right? At the same time, microcontrollers have their own RAM and their own storage as well. So in general, right? I mean, there's two different architectures, right? Harvard architecture, von Neumann architecture, right? So so microcontrollers, right? They have separate memories for code and data. So code comes generally in these days, it's flash memory, which can be erased and written, like 10,000 times or something. Yeah.
We lost you briefly.
Oh, okay. Can you hear me now?
Yes.
Okay. Awesome. So I was just telling that microcontrollers have both RAM as well as flash memory. In flash memory, your program sits in your flash memory and then it runs from there. And then in RAM, of course, you can have your variables and all of that and stuff like that, right? Of course, you don't need to specifically worry about that when you're running a program. So they are generally loaded by the compiler. Generally takes care of it. And also when using a microcontroller, usually you do not you do not kind of use an operating system, right? You're running on bare hardware, right, on the CPU straight away, right? That's one thing, right? So another very popular microcontroller, ESP8266. So this thing has, of course, you can see that it has multiple many pins that can do many different things. Don't worry about what it is right now. Some of this I'll explain later. But the really cool thing about ESP8266, that is super cheap, around 300 rupees or something. And then it actually has Wi-Fi connectivity, right? You can run a full TCP/IP stack on it, and then you can do really, really cool stuff. And this is one of the most popular microcontrollers used by many, many different vendors. For example, there's a very common chip in, say, Wipro smart bulbs and smart switches and all of that. It has very pervasive industrial use today, right? It's actually a pretty powerful chip. It has decent enough RAM and storage for fairly sophisticated programs, right? There's also something we can look at, but we are going to concentrate today on a very famous a chip from a very famous organization, the Raspberry Pi company. So these folks recently released the Pico. It is the latest Raspberry Pi to join the series of devices that they have produced. So far, we've had the Raspberry Pi 1, 2, 3, 4, and then also the Raspberry Pi Zero. But all those Raspberry Pis are full-fledged systems that can actually run a full-fledged operating system like Linux. But the Pico is very, very tiny. It cannot run Linux, or I mean, it can run some operating systems like open source operating systems, but then again, it definitely cannot run Linux because it doesn't have memory protection, for example. Let's not go into those details, but this is how it looks like. Of course, you can see it on my camera feed as well. So at the heart of this is a chip called the RP2040. It's a custom chip made by the Raspberry Pi Foundation. And you have a micro USB port, which you use to kind of connect it to your computer, right? And then you are able to kind of program the chip. You are also able to communicate with the computer. For example, you can actually, if a print statement in your program runs on the chip, you can read it off the USB connection, right? What you're trying to do, right? And of course, there's a boot select button, which allows you to kind of put the chip into special mode. I'll talk about that a little bit later. And there's an onboard LED as well, right? For example, if you look at the camera feed, here's a LED near the micro USB port. Don't worry about that. Again, we'll see it in just a bit, right? Of course, there's a bunch of pins. So these pins are named, 1 through 40. So we'll talk about that as well in just a bit, right? So if you look at this, the Raspberry Pi Pico again, you are able to see that many pins actually have multiple functions, right? Of course, certain pins like, pin 40 and 38, they have a specific, like, for example, this is like where you positive supply is available. This is the ground pin and stuff like that. But you don't have to worry about that. But there are, most of the pins have like many different functions, right? So for example, this 4, 5, and 7, they can be a general purpose input output, or they can be a serial port, or they can be an I2C port, or they can be a UART. I'll explain what those are. So like I said, like most microcontrollers, the Raspberry Pi Pico also has multiple uses per pin, right? So that you can use it in many different applications, right? So this is how the pinout looks, right? So we'll be connecting some pins here and there. So for example, GPIO 15 is actually pin number 20. GPIO 14 is actually pin number 19, and stuff like that. So we'll see as we go, right? So I mentioned some, I said serial port and GPIO and all that. So what does it mean? So if you take any microcontroller, pretty much every microcontroller will have what we call certain peripherals, right? And these peripherals have some use, right? For example, GPIO means digital input and output. What is an output, for example? Let's say you want to glow a light or LED, for example, or you want to drive something using high voltage, or high in the sense, what I mean is that 1 is high and 0 is low, right? For example, Raspberry Pi Pico is 5 volt or 3.3 volt circuit. So 3.3 means high and 0 means low, like 0 is ground, right? So I'll show you how to use GPIO for both input and output. And then there are various serial interfacing components. For example, SPI is serial port interface, and then you have I2C is inter-IC connectivity, right? So that's a standard. And then you have UARTs are called universal asynchronous receivers and transmitters. These are all different types of serial ports. Serial ports in the sense there's usually 1 or 2 wires on which data is transmitted, and then there is usually a clock line. That's a reference line using which you can figure out how data is sent, right? Then there's various timers on the chip itself, right? For example, you can do periodic tasks. We will be using timers in some of the examples that we'll talk about, right? And then there are analog to digital converters, ADCs, right? For you to measure analog data. Look, much of what humans deal with is analog data. And then, for you to interface with the digital world that these chips can understand, you need something that converts it, right? So ADCs generally convert between analog and digital data, right? So, and then of course, we have support for external interrupts. We'll also be looking at external interrupts in this particular talk, right? And then you have PWM, is pulse width modulation. It's a technique used to, kind of look like analog output, but really not analog. It's just a technique, right? So, for example, you want to dim a light. For example, if you have, if you have in some cars, right? These days, I think most cars have this. If you shut the door while sitting inside the car and the lights inside the car start going off, they don't go off in one blow, right? They dim and they shut down slowly. There is a microcontroller sitting in your car actually trying to dim it very slowly down to zero, right? So that's PWM in action right there, right? Apparently, the reason why they did that in the cars was because in the 60s and 70s, if you went to high-end theaters before the movie started, they would like slowly dim the light, and people thought it was a luxury. They associated that with luxury, and then the car manufacturers, especially the Mercedes and the BMWs, they started having that in their cars, and then everybody, of course, everyone else copied them, and now you have like pretty much every car has that particular feature, right? That's PWM in action, right? You can do that using, and very difficult to do using analog electronics, whereas in using digital you can fairly easily do it, right? And of course, you can also, with PWM, you can control the direction of servo motors. Servo motors are motors which don't like rotate continuously. They can kind of go to some direction. Right? For example, you want to like use it in robots, or for example, various driverless cars and stuff like that. You need to control the steering wheel. You need to say, turn the car like 20 degrees or 15 degrees or whatever. You just give the hold the PWM pulse, and then the servo motor can actually, you can control it very, very precisely, right? So PWMs are used for that. And these are the peripherals which are very, very common, not only to the Raspberry Pi Pico, but pretty much any microcontroller. You just search for a microcontroller, and let's say you come across a microcontroller like the ATMega8 is a microcontroller, the ESP8266 or the ESP32. These are all microcontrollers. If you look at their data sheets, you will see these common peripherals, right? This is not just specific to the Raspberry Pi Pico. These are very common peripherals, right? So let's look at what the Raspberry Pi Pico really is in terms of specification, right? So first of all, it's a dual core chip. That's really cool, right? I mean, microcontrollers very recently started going like more than one core, right? And it's actually a 32-bit chip. It's got a Cortex M0 ARM chip in it. There are, of course, 2 CPU cores, and it runs at a maximum of 133 megahertz. It's got 256 kilobytes of RAM, right? I mean, I know what you're thinking. Hey, my laptop has like a 16 GB RAM. It's not even 1 megabyte. What are you talking about, right? But you'll be very, very surprised what you can do with 264 kilobytes. And also the other important thing with microcontrollers is that I earlier told you that they use an architecture where the code and the RAM are, for example, in 2 different memories, right? Like data and the code are in 2 different memories. So, for example, you can have your code up to 2 megabytes. Again, you might be thinking, oh my God, it's just 2 megabytes, but I'll show you what the chip can do. It can do a lot. And the Raspberry Pi is capable of directly running this code from flash without first having to transfer it to RAM. It makes sense, right? For example, if your RAM is smaller than your flash, you cannot possibly transfer everything from flash onto your RAM, right? It makes sense that it's actually able to run the code right from flash, correct? Now, If you look at the support for programming languages, you have support for MicroPython. MicroPython is very, very powerful. It's a re-implementation of Python for microcontrollers or small devices rather. I mean, it runs in a lot of different places, but then again, it's a very powerful re-implementation. It is nothing to sneeze at. It's like real Python. Syntax is exactly the same, and it has some differences when compared to Python, but very, very close, right? Of course, you can also program it in C and C++. There's a separate SDK available, and you can do that. And they have very nice support for Visual C. I'm sorry, it's not Visual C++. It's the Microsoft Code, right? You have support for that as well, right? And of course, you don't need any special power. You can see in the video, I've just connected a micro USB cable. It's connected then to my computer, whatever I'm using. It gets its power from there, right? But eventually, that power is that USB operates at 5 volt, and then there are voltage regulators on board which convert the 5 volt to 3.3 volt, and this 3.3 volt has pretty much become the standard for many circuits today. Many circuits, a vast majority of the circuits actually use 3.3 volts, right? For example, your phone is very likely to be using 3.3 volt as an example, right? And of course, it has USB support. It can be both a device and the host. You can load your programs. I'm moving to the right side column. You can load your program through USB. Basically, what happens is you just hold the. I told you that there's a boot select button on the. You can look at the video. There's a boot select button. It's a very small button. You just, while holding it, if you power it on, it'll show up as a USB disk, USB drive, like a thumb drive on your computer. You can just drag and drop your code. It's that simple, right? It has general purpose IO. It actually has 26 general purpose IOs. We'll talk about general purpose IOs in just a bit. It has three analog to digital converters, 12-bit, that's the resolution, and it tells you generally how accurate you can go, right? And then it has one temperature sensor, which is also 12-bit resolution on the chip itself, right? See, generally what happens is that several chips come with onboard temperature sensors, because if they get really hot, they can shut down to avoid damage, right? So there is a temperature sensor on board, and then there is a universal asynchronous receiver transmitter. It's just a fancy name for a serial port. It's got two of them. It's got two I2C ports. I2C is a very popular protocol. It just uses two wires, one clock and one data, and it's packet switched, meaning that you can have, in just using just two wires, you can connect up to 256 devices, right? It's a very powerful, it's a very simple yet very elegant solution, because what happens is that for every command and data, the address of the device is also sent on the wire, and these devices can figure out if, oh, this command is for me, then okay, I'll respond with the data and stuff like that. So it's a very elegant and simple solution. Again, SPI is there are two SPI ports. Again, like it's again a serial port, very simple to use. It's got 16 PWMs, like pulse width modulation, right? Practically every pin is pulse width modulatable. We'll look at PWM in just a little bit, right? It's got one timer. We'll also be using a timer in this particular talk. I'll tell you what it is. It's also got like a real-time counter, right? It's got some specialized hardware called programmable IO. I won't be covering this, but you can later on figure out how to use it. Yeah, you'll only need it if you're trying to like talk to some specialized hardware which doesn't support SPI or I2C or whatever is there supported by this chip, right? So I don't see a lot of use for it, but it's very, very flexible to have it, right? But we'll not be going into any details in this particular talk, right? And there's an onboard LED which is connected to GPIO 25, right? So we'll also be using it, right? How do you program the Raspberry Pi Pico, right? You have the choices of using C or C++ or MicroPython. for everything, open source SDKs are available, and you have VS Code debugging and simple stepping. That's really, really cool, I thought, right? I mean, so they have a plugin for VS Code. And then, like I said, MicroPython is a parallel implementation of Python. It is not the actual Python, the official Python itself, but then, hey, the language is, almost undifferentiable. And then there is MicroPython supports a lot of different platforms. The Raspberry Pi Pico is just one of them. So if you learn MicroPython, you can apply it to, let's say, we spoke about a bunch of microcontrollers in this particular, during the beginning of the talk. For example, we spoke about the ESP8266, and we also spoke about the ATMega8. MicroPython runs on pretty much every chip that's out there, which is popular, right? And then it's got a powerful runtime environment. We'll talk about that as we go. And I said, generally, you use bare metal, right? You don't use an operating system at all. It's your code is just directly running on the metal, right? And again, there's very early support for Rust as well. But then again, we also have support for some operating systems like Fusix and like RT Thread. These are all open source operating systems which support the Raspberry Pi Pico, right? Installing MicroPython is very, very simple. You just hold the boot cell, the spelling is wrong, BOOT, boot cell button, while powering the boot cell button is right here. You just press it, you hold it down, and you insert, the micro USB cable into your computer, and then it will show up as a USB drive. It'll actually have like a little HTML page there. You just double click and download MicroPython from there, follow the link, and then drag and drop the file into the USB drive. It'll, the Pico will reboot and you will actually have MicroPython installed. It's that simple, right? So, and I'll encourage you to, get the MicroPython, getting started with MicroPython, the official book from the Raspberry Pi Foundation. It's a really, really good book. It goes into a lot of detail, right? So, as that, right? And then look,
Sure. Before we continue, just a few questions. Like Harsha has one question, which is he wants to know if we can run the Raspbian Linux on the Raspberry Pi.
On the Raspberry Pi Pico?
Yes.
Oh, you can't. So the Raspberry Pi Pico is a microcontroller. It's not a full-fledged like a CPU and RAM and all that. Like I said, microcontrollers generally have CPU, RAM, and flash storage on the chip, right on the chip. So I'm pointing to the chip, right? So this chip contains everything. It has the CPU, the ARM CPU, the dual core CPU we spoke about, the RAM and flash and all the hardware peripherals right on the chip, right? So it's not a full-fledged system. So it cannot really run a full-fledged operating system, really.
Okay, thanks, sure. So Ritvik has a question. He says, can we connect the Pico to the Mac? Are the drivers supported, or do we need Linux or Windows?
No, not at all. So you don't need. I mean, I created some 10 examples for this talk, and I did everything on the Mac. You don't need any specialized drivers. It just works out of the box, because usually it emulates the regular USB protocols. For example, it shows up as a drive and stuff like that. So you really don't need anything special at all.
Thank you, sure.
Awesome. So folks, the easiest way to get started with the Raspberry Pi Pico is actually to use a breadboard, right? So now don't be scared of the breadboard. It's like super simple to understand. So you have like what we call power rails on the top and bottom, right? These are connected from end to end. Certain boards have a break in between, and so you can connect them using like 2 bits of wire, and then they'll just get connected through and through. So you can use this for power, the power rails on the top and the bottom. These are connected horizontally, right, from end to end. However, the bits, there are 2 different rows in between. These are connected horizontally like columns, right? So for example, if I were to connect something here, the connection will go right through here, right? So it becomes very easy for us to make connections very quickly. I'll show you, for example, how we'll be using it. And what I've done is I've used a software called Fritzing to show you some circuits, so that it's like a photo, right, of how it should be looking. So it's super easy to use, right? So I just want you to understand that this is how breadboards are connected internally, right? In between, they are all columns vertically connected, and then one row is not one column is not connected to the other. You understand that, right? Whereas here it's connected from end to end, right? We'll see why that is useful, right? So the first thing we'll do is that this is like the hello world of embedded programming. We simply configure a GPIO. So I said GPIO, right? It's general purpose input output. It can be any pin. It can be used for input or output, right? GPIO pin, right? So we will set it to output because we are sending current out, because we want to glow an LED, right? It's very simple because it's all digital. If you set a GPIO pin to 1, you glow the LED. If you set the GPIO pin to 0, you turn off the LED. It's as simple as that, right? Now, the Raspberry Pi Pico has a LED, onboard LED, which is connected to GPIO pin 25 internally, right? Most of the GPIO pins are exposed through one of the pins, right? But the Raspberry Pi Pico actually has a LED which is connected to GPIO pin 25, right? Now, I told you that the Raspberry Pi Pico has 40 pins, and then the numbering starts from 1 near the the USB cable, and then goes around, wraps around, comes to 40. The pin number and GPIO pin numbers can be different. For example, let me go back to this, right? So you see this pin number is 1 here, but it's GPIO 0. This pin number is 15 here, but the GPIO is 11. So don't get confused. So when I say connect something to GPIO 15, I'll be connecting it to pin number 20, right? So, it's just a numbering scheme, right? So the pin number and you always look up. For example, if I say, hey, connect something to GPIO 15, you come and look at this diagram. You just Google image search for Raspberry Pi Pico pin out. You'll be able to see, hey, what pin is what GPIO and what other peripherals, right? Mostly we'll be using GPIO and I squared C. So this is what we'll be doing, right? So yeah, right. So that's what we'll do. So how do we connect this? So this is what I was talking about. So this is how I've connected the Raspberry Pi, right? So if you look at this, this, you see the red line is positive power, and the blue line is negative power, right? And for example, again, same here, and we have the Raspberry Pi. So what essentially we are doing is that we are connecting pin number 20 here, right? Pin number 20 is GPIO 15, okay? We have a resistor because we want to limit the current that is sent to the LED. We don't want to blow it, right? And then, like I told you, look, I mean, these columns are connected, correct? So I'm connecting a resistor in this column here, which means that this resistor then connects to the LED, right? And then the LED then is connected to ground. So if you look at the pin number, this particular pin number, which must be pin number, this 2019 18, pin number 18 is ground, right? Which means negative voltage, right? Oh, negative power, right? Ground is like ground, right? So that's connected here, right? And then this essentially gives negative to the LED, and positive we are connecting through the GPIO, which we can control using our program, right? So how does that happen, right? So let's go to a let me switch screens here. Let me show you the actual code that does it, right? So this is a popular IDE to program, the Raspberry Pi and Pico and all of that, right? So what we are doing essentially, this is super simple, right? So we are connecting an LED to pin number 15, correct? And then, I just have a constant here for pin 15. Then what we do is that we say a machine dot pin and pin 15, right? And then we configure it to be a output. right? I want you to recall that GPIO can be both configured as an input or output. So we are what essentially we are doing here is we are configuring a pin to be the pin number 15 to be an output pin. Very, very simple, right? So we store that in LED, the variable LED. And in a while loop, essentially what we are doing is that we are simply setting the value to 1. This will turn the LED on because we are setting the value of the GPIO pin to 1. And then we are sleeping for a second. Then we are setting the value of that GPIO pin to 0. And then we are going back to sleep for 1 second. So this is a while loop, right? So like I said, there is no operating system, there is nothing, right? So this particular piece of code runs directly on the CPU, and then it simply blinks the LED, right? So let me show you, how this works. Before that, what I'm going to do is that I'm going to change the LED pin to 25, right? We learned earlier that pin number 25 essentially is the built-in LED, right? So you should see it blinking. I'm going to connect the Raspberry Pi to the computer. Okay, I'm going to stop sharing so that you can see my video. I hope you're able to see my video, right? So now let me go and run the code. Are you able to see the LED blinking?
Yes, sure.
Yeah, so the LED is blinking, this onboard LED. So that's connected to pin number 25, right? So let's do something. Let's try and connect a LED to pin number, GPIO pin number 15, okay? So I'm going to take this little LED here, right? And then I'm just going to connect it to pin number 25, but I also need a resistor. I'm going to be using like a 100 ohm resistor to connect it, right? I'm going to stop the program now, right? So so I've connected an LED to pin number 25, so through a resistor, and then I've connected it to ground. So this whole thing is ground. So we have ground negative here and positive here, right? And you switched it. I've changed the code to 25. So let me try running it now. This will see the old code. 1 second. Number 15.
Gautam suggests that the resistor is wrongly connected.
There you go. Thank you. There you go. So you can see that the LED is now blinking. I've switched it to, pin number 20, which is actually GPIO 15, right? If you look at the, so let me share my screen again to figure out, just to make everyone comfortable to figure out what's going on. Let me go back to the presentation. And so what I've done here is that this is pin number 20 and GPIO 15, correct? So I've connected a resistor here and an LED, and then the LED goes to ground, right? So whenever we configure GPIO 15, let me also open GitHub. I can also show you the code from here. It's just a lot easier to see. So this is the code. We are make it a little bigger, right? So essentially what we are doing is that we are configuring pin number 15 as an output, right? So that we want to control the output, right? We don't want to read the input. Output, and because you want to glow an LED, right? And then in a while loop, we simply set the LED value to 1, which will make the GPIO pin go high, which means the LED will glow. And then we sleep. make it 0, sleep again. So essentially this is the program that's running. So as you can see, it's very simple to program the Raspberry Pi Pico. It's like super simple, right? Let's move on. So I hope you understood, for example, how, and like I said, if you change the LED pin to 25, you will be switching to GPIO to, 25, onto which the onboard LED is connected, right? So that was the thing, right? Let's go back. Right. So let's see one more thing, right? So we said, hey, you know, the Raspberry Pi has essentially 2 CPU cores, correct? Now, the trouble with this particular code is that, you know, one core is just busy trying to blink one LED. So can we use the other core to blink another LED, right? That's what we're going to try, right? Let me show you the code for that. It's pretty simple, right? So this particular code here essentially starts a thread, right? So what happens is that whenever you start a thread, MicroPython automatically knows that you want to use the other core, right? And then it automatically uses the other core for the new thread, right? So here's the thread function, right? We are blinking an LED here, and then of course we are also blinking an LED in the main thread, which is our essentially is considered the main thread, right? So we blink another LED there, right? So I hope you understand the code. It's pretty simple. So we use pin number 15, which we are currently using as our output pin. Then we are using pin number 14 for a blue LED. So currently we have a red LED. We'll add a blue LED on pin number 14, right? And then we have the blinking logic is currently in a function called blink an LED, right? We are running the same function in a thread here and also in the main thread, right? And then we are creating a thread here and passing the blue LED value so that, you know, this function can pick up and blink the blue LED, right? So what I'll do now is I'll add another LED and then we'll use the program. So here is one LED I have. This is a blue LED, right? I'm going to just connect it. Just hope and I've connected the LED. Let me go back and run the program now, which is this particular program I'm just showing you on the screen. This will be using both the threads. So I'm stopping the currently running program and starting this program. And as you can see, we have both the LEDs blinking, one red and one blue LED, right? I'm hoping you are able to see that, right? So see, now what's happening is that, MicroPython is on the main thread, it's blinking the red LED so that the first while loop is running in that particular, the main thread. And then we start a new thread, which is automatically scheduled on the other core. And then what essentially happens is that, the other core also starts immediately. That's why both the LEDs are running, blinking simultaneously, right? So yeah, it's that simple to start another thread and utilize another core, and MicroPython in the background is doing all the magic, right? Awesome. So that's like blinking, right? So yeah, so let's go ahead and try and do something else, right? So blinking, yeah. So this is the circuit for the blinking, right? We have essentially we are using pin number 15, GPIO 15 for the red LED and GPIO 14 for the blue LED, as you can see here, right? So see, the problem with am I even sharing my screen? Okay, sorry. Okay, so the problem, yeah, this was the circuit I was just explaining without even sharing the screen. So this is how this is the circuit. So pin number 15 is connected to the red LED, and pin number 14 is connected to the blue LED, right? I'll share the presentation later so that you guys can try out all these things. So see, the thing is that, we are actually utilizing cores to do something very trivial as blinking LEDs, right? So what if there were a more efficient way to do it, right? So if you want to do some periodic tasks like blinking an LED, or you want to clean something up or whatever, right? So you can use timers. We know that the Raspberry Pi Pico actually has one timer, and we can use it, right, to blink LEDs, for example, right? And in the previous example, both cores were tied up for a very simple task, right? But you can use hardware. So the Raspberry Pi Pico actually has a hardware timer, right? And whenever a timer expires, it can create an interrupt, and then it can run any routine you want, right? For example, think of it like a callback. It's not really a callback. Calling it a callback is ridiculous, but it's like a callback. Whenever a timer expires, or you say, hey, the timer expiration is 1 second. So the timer will expire every 1 second, and it will kind of call a interrupt function. It's like a callback to kind of trivialize things and oversimplify things. But then the beautiful thing is that it frees up the CPU, because the CPU can continue doing more other tasks, right? And then what can happen is that whenever you want to do something, periodically, you can use a timer interrupt to do it, right? And timer interrupts are actually used by operating systems, for example, as TCP/IP timers to retry sending packets, or to actually do task switching itself, and stuff like that, right? So we do all kinds of stuff using timers, right? But let's look at an example here where we are actually using a timer to blink an LED, right? Oh, before that, 1 second, I want to show you something else, right? Okay. Now you can see that both the LEDs are blinking simultaneously, correct? What if I told you that you want to, the LEDs need to kind of blink one after the other, right? So you can do something used like a very nice mechanism. It's exactly the same program as before, but we're actually using a lock, okay? Think of this blink and LED function as a critical section, okay? Only one thread can have access to it anytime. So what we do is we say, hey, lock acquire, blink an LED, and release the lock, right? Now for the duration that this function is running, only one thread can actually be in the critical section, right? This is really, really amazing, because underneath what is happening is that between the two CPU cores, MicroPython is setting up a shared lock and then managing it completely for you. This is almost like magic, right? So let me, for example, stop sharing my screen so that you can see my video. I will show you. I'll run that particular program now. Let me stop this. Right, this is stopped, and let me run this synced. Yeah, as you can see now. What's happening is that essentially, only one function can, when it holds the lock, it can actually call blink an LED, right? And then later on, it has to relinquish the lock for the other function to be able to call blink an LED, right? What's actually happening on the hardware is that both CPU cores are beautifully being synchronized, right? And MicroPython makes it ridiculously easy for you to be able to do that, right? So I think this is really, really cool. And MicroPython, all kudos to MicroPython. They made it like super easy for you to do that, right? Awesome. So now let's go back to the timers example. So in the timer example, we were seeing, hey, this is, yeah. This is the fourth example, right? So what essentially we are doing is that look at our, forget all the function definitions and all that. Come and look at this while loop. We are no longer blinking the LED here, right? We are simply sleeping and printing something. And this will show up on the console, right? I'll show you that, right? And then what we are essentially doing is that we have a function, which this is called a interrupt request handler. So what we are doing is we are setting up a timer here to go off every 1 second, right? This is in milliseconds. So, and this is a periodic timer. You can even set up timers for one shot. They'll fire and then it will never rearm the timer, okay? Here the timer is rearmed periodically, meaning that every 1 second the timer expires, this function gets called, and then the timer is rearmed so that it can get called again, right? So, and then we are saying, hey, this is the callback, right? So this callback here, right? So now what happens is in the callback, we are using a new function called toggle, right? So this is a GPIO function, right? So what happens is we are setting up this LED as a GPIO out, right? And then of course timer is, again, we are saying machine.timer. This will set up the hardware timer, initialize the hardware timer for us, right? So and then, hey, here we set all the details of the timer, right? So essentially what's happening is that we are simply toggling the LED. We don't know what value it is. If it's 0, it becomes 1. If it's 1, it becomes 0, right? Very simple, right? Let me run this now. I'll share my screen. I'll share the editor. Right. You're able to see the editor, right? So this is the timer. So here you can see whatever we are printing comes out. I will need to, 1 second. Connecting to the hardware.
What is this? What did you say this ID was called?
THONNY. That is
Okay.
they recommend that people use this. Okay. Yeah, one more thing I found is that,
I see it at the top of the screen.
Yeah.
Please go.
Yeah, whenever you use the lock, then I see that you have to reset the device. I mean, you have to pull out the USB cable and put it back in. For none other example, this happens. So this consistently happens with this example. Anyway, I just pulled out the USB cable and reconnected it back. Right now, folks, the other thing is whenever you use print, you have to realize that this print is running on the device, on the Pico, right? And then what happens is that through the USB cable, the data, whatever you print, is sent out so that the IDE can display it. That's what is actually happening, right? So let me run this example, right? Now you can see that the red LED is blinking. Hopefully you can see that in the video. The video is really small, but then again, I'm printing out, this. So we have a timer, we have a interrupt handler here, which gets called every 1 second. We are simply, incrementing a global variable, and then we are toggling the LED. This is also new. This is the first time we are seeing this. And while the main thread itself doesn't really blink the LED, right? The timer interrupt handler is what is blinking the LED, right? And you can see that it's printing something. It's basically printing the value of the global variable called timer calls, which is being incremented by the interrupt handler, right? So you can see that, you can see this output here, right? I hope you understand this. So essentially what we are doing is that we are asking the CPU to, essentially what is happening is this particular code is your main thread, right? It keeps running on a particular CPU core. And what's happening is that every timer interrupt, the CPU is interrupting this code, right? And then it's saving the context, going to the interrupt handler here, running the interrupt handler. Once the interrupt handler is done, it is restoring your main thread and letting it run. So every 1 second, this exactly is what's happening. So we are using the hardware facilities that the Raspberry Pi Pico provides, right? So that's kind of cool, right? So we now have a while loop. We can do whatever we want, but then automatically what will happen is that the LED will keep blinking no matter what you do here. You can be in a tight loop here, doesn't matter. Hardware, the CPU can interrupt your code and run the interrupt handler and restore your context and make you run again, right? I think this is really, really cool stuff. And especially you're doing this without any operating system at all, right? Awesome. So
sure, I have a question.
Yes.
Is that while loop necessary?
I think if you do not provide a while loop, then there is a while loop in MicroPython itself. So okay, you might want to experiment and see. See, okay, the while loop here is really a placeholder for me to say, do something cool here.
Right.
Right. So you're doing something there. We don't know what you're doing. Maybe in the future, you're pitching weather and you're doing something really cool. You have some Wi-Fi interface. You could do something funny, right? So you're doing something. I'm just hoping you're doing something nice, right? So, but the whole idea is that to do any periodic tasks, you don't have to, let's say you have really complicated logic here, and then you also need to blink a LED. That becomes very painful, correct? Right. So the idea is that with a timer, you can kind of do periodic tasks very easily. And then whatever it is that your main core is running, it'll automatically be taken care of by the CPU, because it's kind of now that's how interrupts are handled, right? This is an example of a hardware interrupt.
Right. So Akash has a question.
Okay.
I think he wants you to code live. His question is, can we use input from a proximity sensor and control the LEDs based on the sensor data? Now,
yeah,
I think you told me that you're going to use the temperature sensor.
Yeah, I actually, I have a very close example to that. So I'll come to that. Yeah, I have a very close example to that, right? So awesome. So next is I'll continue to share this particular screen because I need the screen for the next example. So in the presentation, we saw that the Raspberry Pi has an on-chip temperature sensor, right? So in this example, we are going to read it, right? So we also specified that the Raspberry Pi has, I think, about 4 different ADC, that's analog to digital converter channels, and then the on-chip sensor, on-chip temperature sensor is connected to ADC channel 4, right? So we just do machine.adc. It's a Python, MicroPython built-in object within machine, right? And we specify the port, we specify the channel 4, right? I'm not going to the details of what is the conversion factor and for example, why are we dividing and all that. You can figure it out. ADCs are very simple devices. You just need a conversion factor. You can figure it out, right? But the main thing here is that you are setting up ADC. You are setting up an object for ADC channel 4, which is sensor temp, right? And then we simply do sensor temp dot read U16. So we are reading a 16-bit integer here. We are converting it to degree Celsius here, and then we are simply printing it. So printing means it will show up in the console, the serial console, right? So let me just run this, right? So instantly you see that every 2 seconds it's printing, the temperature is 28 degrees. It's kind of accurate, but not very accurate, right? So this is what the chip thinks, Yeah, so I hope you're able to see the chip temperature output, right? Which we are printing here, right? Awesome. So this is how you use ADC. Okay. Now let's see something more interesting, right? Let me stop sharing and let me start sharing my presentation back to the presentation. Okay. Now let's come to this, right? This is very interesting, right? So how do we, you saw that we could use GPIO for output because we wanted to glow an LED, right? So that was output, right? From the chip. So you always think of GPIO from the perspective of the chip, right? So when you are a chip, hey, you want to glow an LED, you send LED some voltage, right? Of course, you send it some current, right? So that's output, right? But what if it were input, right? So like I said, hey, GPIO is general purpose input IO, input output, which means that you can use it for input as well, right? So all GPIO pins on the Pico have this is very important, folks. So let's say that you want to read a GPIO pin state. Okay, what is a state? It can be either 0 or 1, right? So it's like a GPIO pin is simply like a variable, okay, and it's memory mapped. You don't have to worry about it. Every GPIO pin has an address. You just read that address, you get a 0 or 1, right? But in hardware, it's not that simple, right? So in general, all pins are supposed to be in a floating state. That is, they're undetermined. The state is undetermined. Okay. So what you have to do is there is a built-in. Every GPIO pin has a inbuilt resistor. It's programmable, that resistor. Okay, I'll tell you why it's interesting, right? So you can set that resistor to pull up or pull down, meaning that particular pin, if you pull it down, it means you're setting the value to 0. It will be connected to ground. Okay, if you're pulling up the resistor, that particular pin value will become 1, which means that you're setting that particular GPIO pin to 1. Okay, that is you're giving it 3.3 volts, right? It becomes 1, right? So let's say that you have to make a particular GPIO pin read the state of a button, push button. Okay, so let's say that I have to connect. I'm connecting the button to VCC, which means that 3.3 volts. Okay. So now what will happen is, if I press the button, this particular pin will become 3.3 volts, right? Now, if you have to read that as a 1, you have to set that resistor to pull down. So what I'm doing essentially is, it's very simple. I take a particular pin from which I want to read the state of a push button. Okay. Let's say that is pin number, let's say 13 or something like that. Okay. So what I do is I connect a push button to it, and then I connect the push button to VCC, which is 3.3 volts. Okay. Now, whenever the button is pushed, that pin will go high, that it will go to 3.3 volts, right? And then for that to happen, I'll program the programmable resistor to pull the pin down so that we know the state of the pin. The state of the pin will become 0. Whenever I push the button, the state of the pin will become 1. It's very simple, right? So, and we can poll the pin for activity. I want to talk to you about bouncing. I'll tell you what bouncing is when I show you what we're talking about. Let's see the code. Right? This is the code, right? So essentially, so far we set the pin to out because we were glowing an LED, but this time we are setting it to in because we want to read the state of a push button, right? And then we are saying pin dot pull down, right? Which means that we are programming the internal resistor to pull the pin down to 0. When you press the button will make the pin go high to 3.3 volts, which will be read as a 1 when you read the memory mapped variable which corresponds to the pin, right? That's what is happening actually, right? So, and again, we have a LED as well. Of course, LED, we need to make the, pin, set the pin to output mode, right? So that's what it is, right? And then, of course, we have a simple loop where we are polling for the button's value. We are constantly seeing if it's 1. See, this is a while loop. It will run as fast as it can, right? So we are constantly checking if the value of the button is 1, which means you press the button, right? When you press the button, the value of the pin goes high. It will be read as a 1. And then, you toggle the LED whenever that happens. And whenever that happens, you sleep for a little bit because whenever you push the button, right, button is made of metal, right? It will bounce, but the CPU is really, really fast. So every button push, it can actually register as many button pushes. That's why we sleep a little bit. This is called debouncing logic, right? You don't really realize this, but then every electronic circuit in which there is a button has debouncing logic, because whenever you push a button, you don't want that function to happen 100 times, right? But you don't realize that because CPUs are super fast, right? They can like be this CPU can be doing like millions of instructions per second, right? So and GPIOs are very sensitive. They can pick up every bounce of the switch, right? So this is called debouncing. This is a very stupid debouncing logic, but hey, it works, right? So what I'll be doing now is pin number 13, right? So I'll be connecting it to the button, right? One button. So what's the button, right? Let me show you the screen, right? Let me switch back. So this is a push button, right? Very simple button, right? When you push, you just connect two wires, right? I'm gonna connect it here, and then I'm going to take a little wire, like say this wire, right? And I'm gonna connect this to. Let me check which pin number I'm supposed to connect it to.
While you do that, Shuveb, just a quick time check. We're in the last 20 minutes or so.
I'm almost done, so.
Okay.
Yeah, this is to GPIO pin 13. And I'm gonna run the program now. This is the polling program I just showed you. So whenever I press the button, we toggle the LED. I hope you're able to see that.
Yes, sure.
So we're using GPIO for input now, right? Essentially, that's what we did, right? Now let's look at right another efficient way of doing this, right? So see, what we are doing now is that we are kind of yeah, this is the circuit for the button sensing. We are polling we are polling the button, correct? So if you see here we are in a tight loop. We are seeing whether the button is constantly, whether it's one, right? That's a problem, right? I mean, if you have to do something else, you cannot be doing this. And then if you're busy doing something, but then you don't want to miss that somebody pressed the button, right? So you can do something, you can definitely do something better. You can actually do you can set up an interrupt on the IRQ sorry, on the GPIO pin, and then there's a much better way to handle this, right? So this is the exact same program, but essentially what we are doing is that we are adding this one extra statement here. We are saying that, hey, whenever this pin goes high, you simply call a callback, right? And then in the while loop, you can do whatever you want, right? That's the whole idea. And then in the callback or the interrupt handler, to be precise, we actually toggle the LED, right? This is much better way of doing it, right? So there's no difference in the circuit, it's exactly the same, but there is a world of a difference when comparing these two programs, because this program is a lot more efficient. We are letting the CPU do the polling for us. We are not polling it in code, right? That's the difference, right?
I noticed you don't have a sleep in the interrupt handling case. Why is that?
You don't need a sleep, because this function is only called when the button is pressed, and then nothing happens, right? I mean, you return to your main while loop. So your while
I
loop is
see.
what is running continuously, or interrupted whenever the button is pressed. You execute this function, and then you're back to your while loop, your main thread.
So we don't have to worry about bounces when we use an interrupt either.
Uh, you, I, that's a good question. So GPIO, what do you call, bouncing is always tricky. So it depends on what the manual says. Some folks in GPIO, they do the debouncing logic, on the chip, or the runtime can do it for you. It really depends, Vijay. In the Pico's case, I really don't know how it is set up.
Okay, thanks, Shuveb.
Awesome. Let's move on. I only have a couple of things more, and so let's get a little serious. So what we'll do now is we'll connect the LCD, right? And then, we were earlier displaying the temperature on the serial console. So I have a little LCD panel here, and this is a very simple panel, and it uses what is called the I2C protocol to connect. It's only two wires. So you see four wires here, right? Two are for power. One is ground, one is power, right? The other one is called SDA, and one is serial data and serial clock, right? So only two. So it's very, very simple. Let me hook it up. I'll show you the program, right? It's super simple. Of course, I'm using a library to control the LCD itself. But then again, what happens is that, we we set up the I2C, right? So we use pin number 0 and pin number 1 to set up I2C, and then there's a LCD library. We configure this is the 27 is the address of, I told you that I2C uses an addressing scheme. So 0x27 is the address of the LCD, the chip on the LCD, right? And then, of course, it's the exact same program. Rather than printing to the console, we are actually showing it on the LCD screen, right? Let me try and connect the LCD screen. I'll first connect power. It turns on, as you can see, it just starts glowing green. And then let me connect these two. Yeah, that's connected now. Let me run this program for you. Yeah, I hope you're able to see it. So we are displaying the chip temperature to 28.92. So this is the on-chip temperature, rather than uh, you know, rather than kind of um, displaying it. I mean, printing it to the serial console. We are showing it. Let me. Oh, I'm still sharing my screen. Sorry about that. So I hope you are able to see the video now. So rather than sharing the, printing the temperature on the serial console, we are now displaying it on a LCD screen, right? So you're able to see that. So let's get a little, this is the last one. Let's get a little bit more adventurous. Let me share my screen again. Let's look at the code once more. It's a super simple code. You can see that it's fairly easy to, connect and actually use something as complicated as an LCD. We are using I2C is a type of peripheral. It's just a bus which uses 2 pins. One pin is for the clock to synchronize between the LCD and the chip, and the other one is the data pin 0, right, which actually sends the data to the LCD, right? And then, like I said, using just 2 wires in I2C, you can connect multiple devices. So the idea is that every device has an address, right? In this case, the chip on the LCD has this particular address hex 0x27, right? And then we configure the LCD. It has 2 rows and 16 columns, right? So that's the LCD configuration. Again, this code you're familiar with. We already saw this code. We are reading the temperature. We are clearing the LCD, moving to 0, 0, column 0, row 0, forming the string to print, and then we are simply saying LCD.put string, and then we are sleeping 2 seconds, and we are continuing this. So we have a beautiful display, which it's a self-sustained system now, right? You don't need a computer or anything. You can just read the temperature of the chip, of course, right? So let's get a little bit more adventurous, right? So we did this, and then hey, of course, I told you how the chip itself works. This is the wiring diagram. But let's look at connecting one more sensor, right? So this is called, I'm using something called the DHT22, this particular chip you're seeing on my video. This is called, this is a temperature and humidity sensor, right? The temperature and humidity sensor essentially can read both temperature and humidity. It uses a custom protocol, but then drivers are available for the Raspberry Pi Pico. Once you connect it like this, you will actually be able to read it and display it. Now, we are currently using the chip to essentially show the on temperature from the on chip temperature sensor. But then let me connect this as well, right? It's a very simple thing. It uses a single wire protocol. So it has basically 3 pins. One pin is negative and 2 pins are for power, negative and positive, and then another data pin, right? So let me connect it up for you. I've connected it now. I'm going to run this program. Yeah, and you can see temperature and humidity from the sensor, right? So temperature is 30 and humidity is 63. That sounds about accurate, right?
Sure. I noticed that the temperature went up after you connected the device. Is that because it's processing more right now?
No, Vijay, that is because of let me do this, right? So let me run the previous example, which uses the on-chip sensor. Okay, the on-chip sensor thinks it's 28, but the DHT22 thinks it is 30.2, right? So the DHT22 is likely to be more accurate because it's a much more advanced chip. Actually, it's pretty expensive also for a, sensor. It's like, I think it's around 300 rupees or something. It's pretty accurate. DHT22s are highly regarded as pretty decent sensors, right? And the a single sensor, we have both humidity and temperature, right? So that's like.
So if you blew on that sensor, would the humidity change?
Actually, I don't want to try that, but yeah,
okay.
Maybe we can try. Yeah, there you go. It's actually changing. It went to 70.
Like sure.
Yeah, awesome. Man, you are making me test like other people's hardware. I don't know why you do that, but anyway.
I told you
Awesome.
I'm a software guy. I wouldn't play with them myself.
Yeah, you don't want to trust anything. Yeah. So anyway, let me start sharing my screen. We are done. So we looked at like 10 different examples. Awesome, folks. So this is the DHT22 wiring diagram. So it's very simple. You have positive and negative going to the DHT22, a single data wire connected to 13 GPIO 13, and that's it. That's the wiring. You don't need anything else. Super simple stuff, right? So here are some closing thoughts. So this is something I worked on, I think, exactly 10 years back, 2011. So we were solving a real problem. For example, there was a server room, and sometimes the server room was running really, really hot, and we wanted some kind of a notification mechanism and a way to monitor what's happening in the server room. So I built this particular device. So it uses a ATMega8 It's a very powerful device. It's usually coded in C language. It can run MicroPython as well. So here is some Ethernet circuitry, no Wi-Fi and all that those days. So here's a power circuit, right? So I haven't, in this particular picture, I haven't yet connected the temperature sensor, but eventually that's what happened. I connected the temperature sensor, and then this had IP address, and it had a little web page, right? And it had actually running a full-fledged web server, and it displayed what the temperature in the server room was. That's it, using a web page, right? And then you could do /JSON or something, and it would give you JSON, and you could do some really funky stuff with it. So this was 10 years back, and then I solved like a real world use problem, right? Because I really wanted to know what the temperature was, because there was some very expensive storage equipment running in that particular server room, right? So right now I'm building this. So weather monitoring system. I have one this beautiful LCD, and behind this is the ESP32. It's a very popular microcontroller, and then one of this is outside. So this is the front and this is the back. So it can have like a huge battery, and it can practically run for months or even 1 year. Again, it senses temperature, produces JSON on a particular IP address. So this particular little guy here displays the current weather inside the room and outside weather from this particular device, which is also on Wi-Fi. Right, both are on Wi-Fi. So you can do that. So I'm just building it right now. But you can extend this. For example, let's say that you want to sitting at home during your weekend, you want to keep an eye on your service. What is the latency, right? If Freshping gives us an API, you can actually graph it, and you can create some cards. One card will show you one service, then it changes, the card changes, and another service shows, and stuff like that. So you can do some really, really cool stuff. I actually used to do that years earlier. I used to have a little system called the Chumbi sitting. It was a little different. I wiped out the software and I kind of wrote my own software. But then this is something that you can really do. I am working on the weather station something. Right, and then where from here, C is a great language, but Python is widely used. You can even try Rust on embedded systems. I really want you folks to look at the ESP8266 and ESP32 microcontrollers. So both of them can also run MicroPython, and they are very, very powerful because they have Wi-Fi capability. You can run web servers on them, and you can do like really, really cool stuff, right? And take a look at the real-time operating systems, and take a look at Adafruit and SparkFun. They are really, really good resources. In India, you can go to robu.in, robu.in. You can buy all this hardware. They send it to you in a couple of days. Right? So yeah, so thank you very much. I hope you really liked this, and then it inspired you to look at you know your own way to kind of get started with hardware. It's a combination of hardware and software, so it's always interesting, and you can do some really cool stuff with it. Thank
Thank
you.
you, Shuveb. So I'll just ask you some of the questions from the Q&A. The first question that I'm going to ask is something I think the bulk of us have as a question to you, which is when do you get the time to explore all this? Is there some project internal to Freshworks where it is used?
No, I don't think Freshworks uses any embedded systems or anything. At this point of time, at least, I don't know of. Yeah, but I mean, I started with embedded systems, my career at least, and then we used to do a lot of this stuff. And I don't know if Naveen is on the call. Naveen Sylvester and I, we used to, the way we learned embedded systems was we used to build these for engineering projects for the students and all that. So we we used to do that. It was a lot of fun. It was not about the money at all. It was more about learning. And those days, the devices were very different. We had to like shine UV light on them to erase them. And we didn't have the equipment. We used to take a cycle and or whatever we had. We used to go to another place like electronic shop, and they used to every time they used to charge us 50 rupees to do that. That was like a real pain because if you like had some bug in your code, then 50 rupees gone, right? So not forget about the 50 rupees. You had to like go somewhere else and imagine how clever you had to be while writing the code, right? So that's how we started, and then I have kept in touch with embedded systems, and I have a lot of electronics in my house. So yeah, that's how I keep in touch.
So Gautam has a question. Gautam, your mic is enabled. You can actually ask it.
Yeah, hey Shubha, great presentation. And I think my question is pretty much answered, but let's say I have a 12-volt motor, right? So servo motor or a 12-volt device, external device like a lamp or something that operates on 12 or 24 volts. But Pico will be operating under 3.3. So how can I control those? So I mean, will using a relay help?
That's exactly right. Yeah. So there you have a couple of choices, Gautam. So recently I bought myself something called a triac circuit. So what exactly? So relay is one thing you can do. For example, you can buy a 3.3 volt relay, and relay is basically think of it like a switch, but you can control it through GPIO, right? But the switch itself can handle a lot more voltage. So that's one way to do it. Or you can also use a triac. So recently I bought myself one because I have a LED strip, but I'm also using PWM. That's the beauty about triac is that you can use a PWM to control it. So meaning that it's just not on or off. You can also, you can also do like much more funky stuff, right? So what you'll be able to do is that you can like, let me share my screen and very quickly show you folks. Yeah, so I recently ordered this. It's on the way. I can't wait for it to come. So if you take a look at this, right? So here is a PWM, right? So let me see if I can. Oh, how do I? Awesome. So you see this here, J1. This is where you provide PWM input, and then here you provide. I think this can do up to 36 volts, so it can control LED strip lights easily, right? So mine is like a 12-volt LED strip light. So this you input 12 volt here, and then you connect your device here. So this is input, this is output, and you have PWM here. So from PWM you can go from 0 to 12 volt, but you can slowly go. You can be in between. You can do whatever. That's how you control the brightness of the strip light. Actually, that's how all the strip lights, like which are able to control brightness, actually work. So this device is like 100 rupees or something like that. You buy this, you connect the ESP32. The ESP32 can connect to Wi-Fi. You write a simple web server. You can connect it to Alexa or Google, whatever, Google Home and all that. And using voice, you can control your LED strip. It's as simple as that.
Right. So relays are pretty much outdated.
Relays, you can, for example, if you want to use like a real 230 volt device or something, you can still use relays. Relays all the time. You see some smart switches behind me, the large ones, those actually use relays to control like full-fledged devices.
Okay.
Yeah. Okay. You can use relays. Relays are good devices. Yeah.
Yep. Thanks a lot. Yeah.
Hey Shuveb, Saju here. Question. Very inspiring talk. So I use a Raspberry Pi 3 with the Raspbian OS, and we generally SSH into and we write Python code.
Yeah.
So question here is with the Pico, we write MicroPython. Does it support importing of all the regular Python modules which you find in Pi?
No. So I mean, there is. They try to keep the names of the modules same in some cases, but then again, the most popular module for MicroPython, Saju, is the machine module, which contains all the hardware of the machine. They abstract it out, right? For example, machine.timer, machine.pin, which is like a GPIO and stuff like that. So yeah, you have like different modules here, but the more important thing is the language, and everything else is exactly the same. Once you get the hang of MicroPython, it's not very different from using regular Python at all.
Yeah, so this most simple use case, like sending a HTTP request where we used a request module, what would be the equivalent in MicroPython?
I can't recall, Saju, but then again, there are like full-fledged web servers available. I think the HTTP module is there, if I am not mistaken. But then again, you have full-fledged web servers which are built on top of MicroPython completely.
Sure.
Yeah, especially for the ESP32 and ESP8266, very, very simple. You can easily run a web server example is usually probably 10 lines of code.
Okay. Thank you.
Thank you.
Okay, so last two questions. One from Hemchandra Shuveb. The question is, do we need to explicitly manage power utilization and sleep cycles to get battery mileage?
Awesome question. So, for example, I was telling you that, hey, I plan to have a small IoT device outside the house which connects to Wi-Fi, and then I want the battery to last months. So I cannot use sleep, or I should not be using a while loop anywhere. I shouldn't do it at all, right? So I should probably be waking up, sending some data, or doing something and going back to sleep. And many of these devices support something called sleep modes, right? So there's a deep sleep mode, and they'll tell you for each mode how many microamperes or milliamperes the device actually consumes, right? And then MicroPython makes it very easy for you to handle these sleep modes, so and stuff like that. So you can absolutely, you can, like I said, you can have devices running on a battery, and then these can last like very, 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 very long time, months actually, and you can put them in these deep sleep modes, and these work really, really well.
Thanks, Shuveb.
Thank you.
Prakash has a question. Prakash, do you want to ask?
Yeah, so what's the major difference between Raspberry Pi 3B Plus and Pico?
Okay, so Raspberry Pi is full-fledged. I mean, it can run full-fledged operating systems. It's more of a traditional computer. Meaning it has a CPU, it has a RAM, it has storage in terms of SD card and all of that. Whereas the Pico is a microcontroller, meaning that on the chip you have everything. You have the CPU, you have the RAM, you have flash, you have all the peripherals we spoke about, the I2C, S-port, SPI, UARTs, and all that good stuff, right? It has on a single chip, right? So that's how that's the difference. But it has like very, very, I think it has 256 kilobytes of RAM or something. It cannot run Linux or any other not multitasking, rather multi-user operating systems. You have specialized, really tiny operating systems that can run on the Pico, Prakash. So yeah, I mean, you cannot run Linux or any other operating system that currently runs on the Raspberry Pi. It's just the architectures are very different, and also the resources are very, very less and few in the same.
Yeah, sure, thanks.
But it's a lot cheaper, right? That's the whole idea. If you want to control hardware, you want to make let's say 1,000 copies of some kind of IoT device, and you want it to be really cheap, you'll be looking at the Pico, not at the Raspberry Pi, because for controlling general hardware, you want to make a smart switch or a smart lamp, you will not be looking at the Raspberry, general Raspberry 3 or 4. You'll be looking at the Raspberry Pi Pico. That's all you need actually, right? So, or the ESP32 if you want Wi-Fi and stuff like that.
Okay, so I thought we would stop with that because we are over time, but this question is too good to pass off. It's an anonymous question, so I will read it out. The question is, what is the fun in coding in Python? Shouldn't we just code using registers?
Look, I mean, by all means, right? For example, if you are interested in C, you can go to a low level, or if nobody is stopping you from using assembly, ARM assembly, right? So you can learn ARM assembly. There are many tutorials which will allow you to write ARM assembly and then run it what do you call? Ultimately, right? I mean, if you're using GCC, the code gets turned into assembly language anyway. So you can directly write it and you can run it on the Pico. Nobody is stopping you. Like I said, the C SDK, C++ SDK is available. It uses VS Code, and then you can certainly try it out. You can go as low level as you want.
Okay, I think we are like well over time here. Thank you so much, Shuveb. That was a lot of fun.
Thank you, folks. Have some fun with hardware. Yeah.
Thank you.
Bye-bye.
Bye-bye.